everyone, and welcome to another episode of the Data Science Decoded podcast. And today I'm here with Mike. How are you, Mike, today?
I'm okay, feeling good. The weather is a bit cold in Israel now, but
Yeah.
I was born in a quite cold place, so I know how to cope with it. So let's talk about this paper from the School of Aviation Medicine. I think it is the first paper which we are discussing from the School of Aviation Medicine. By the way, maybe our listeners don't know, I was my first and second degree, my BSc and the MSc, the first MSc was from Moscow Aviation University, or I don't know how it is called now. Then I studied when I studied there. It was called the Moscow Aviation University, so now it may be another name. So
yeah, it says here Air Force. I think the authors of the paper did work for the Air Force on, like, that's my guess, something related to understanding or which people could become pilots or something like that. So I think they had like data which is medicine, like some features that are about their height, weight, whatever, and they needed to decide if they are good for to become pilots. But that's my idea. If we scroll down to our listeners, the name of the paper is Discriminatory Analysis, Nonparametric Discrimination, Consistency Properties. And this is the first paper that introduced the concept of K nearest neighbors, right? So that's why it's seminal. It's from 1951, I think. Let's see if it says here. Yes, 1951. And the authors are Evelyn and Hodge Jr., and they both PhDs. As far as I remember, I checked, they both became professors of statistics later in their life. So this is right a year after the PhDs, both of them. They think they like went to serve in the army or something like that.
It is interesting, by the way, if the Berkeley PhDs today are writing papers for the aviation journals. I'm not sure. Maybe some of them do, but
so it's not an aviation journal. It's just like
aviation.
They did the work for like the Air Force, and that's an internal document that was released. You see, project report.
I see, it's project report.
It says approved for public release.
I see. Distribution is unlimited. I see it here. Yes.
Yeah, so they worked on some internal project and released it.
Yeah.
Okay, so I'll read the introduction, which will explain the problem that they're trying to solve. So they say the discrimination problem, two-population case, may be defined as follows. A random variable z of observed value small z is distributed over some space. They say, let's say the p-dimensional space, either according to distribution f or according to distribution g. The problem is to decide on the basis of z which of the two distribution z has, right? So it's in a sense like a classification problem. We get data point z. We need to say if it's coming from G, one distribution, or it's coming from F, another distribution.
Yeah, I have a very small remark. I try to synchronize our listeners. The simplest case of this problem is the Gaussian mixture, which is composed of two Gaussian distribution. What is Gaussian mixture? Gaussian mixture is a weighted sum. I can say it's not weighted sum. It is a random variable, which is the probability p is distributed according to some normal distribution, and the probability 1 minus p is distributed according to another probability distribution. And the simplest case for this problem is to decide from each one of these two distributions the current sample was taken.
Okay, yeah. So it's like dovetails in what they say. There are three types of problems where F and G are completely known. So this is what you said, right? You know a priori that F and G are a mixture of Gaussians.
Not necessarily, by the way.
No.
They can be completely known. This is the simplest case, but it can be from the case 2. It looks similar to 11, but I guess it is a Roman number.
It's number 2. And it says F and G are known except for the values of one or more parameters, meaning it's like a Gaussian distribution. So you know the mean and you know the variance, for example.
But here for the second one, so sorry, I want to explain for the second case. For the second case, F and G are of the Gaussian distribution, but we don't know the expectations and the variances, and it is possible to find them, to estimate them.
Yeah, and another case, number 3, that they say where F and G are completely unknown, except the possibility for assumption about the existence of densities, meaning you just know there is some distribution F and G and that's all. And in this paper, they're trying to tackle this case. So that's why it's called the non-parametric way of doing that, because you're making zero assumptions about the distribution of the data. And they say here, subproblem 1, when they're completely known, is completely solved. The solution is implicit in the Neyman-Pearson lemma. They've referenced paper number 1, which is similar to what we reviewed. We had a paper by also Pearson and Neyman. It's not the paper that they cite, but almost the same year, which uses maximum likelihood. Right? We reviewed that paper, so it's like one of the first episodes. And actually, they cite 3 papers. The third one is also a paper we reviewed by Fisher. Yeah, with the IRIS database.
Yeah.
Where he did like linear discrimination. And then they try to generalize now to non-parametric discrimination, or in a case like 2-class classification problem.
By the way, Daniel,
you want to say it,
one small thing. Maybe we will remind our listeners what is the difference between parametric and non-parametric assumptions.
In the
parametric assumption, we not just assume the existence of some probability distribution of the samples we are observing, but we assume that we know the formula for this distribution. We know the form of this distribution. For example, it can be normal distribution, it can be Poisson distribution, and then our task is to estimate their parameters. And in the jargon of machine learning, they are hyperparameters. In the case of non-parametric distributions, we make zero assumption about distribution, so we assume it exists, and we don't know anything. So we try to do some estimation without an explicit form of this distribution. There is no parameter. So we still want to understand to distinguish between 2 different distributions, but we have zero assumptions about their form.
Perfect. Thank you for that. And they say here, if we know, so this is the paper by Neyman and Pearson. So if you know something about the distribution of, let's say there's F and G, 2 different densities, so you can do maximum likelihood, right? So let's say a point Z is coming. Now it's like you want to evaluate it if it's in F or G. If you have those distributions, you do the ratio of Fz divided by Gz, and if it's like greater some constant, then you say it's probably class F. If it's less, this is the constant, it's in class G. Right? Again, if somebody wants to dive deeper, we had this paper reviewed at the beginning by Fisher, by Neyman what's their name? I forgot again. Pearson-Neyman, sorry, yeah. So which, in a sense, it's maximum likelihood.
Actually, it is a bit, even a bit simpler than the maximum likelihood. It's just a likelihood, not simple, but it is a likelihood ratio. You know, we love to use log likelihood ratio in almost every paper about deep learning or machine learning. We have some log likelihood ratio. Here we have a likelihood ratio. For example,
it's not log.
Yeah. It is. We don't have log here. We don't need log here. But if we had log, we need to make it less. C will be equal to 0. No, not equal to 0. In the case C equals 1, which is the default case for me, you just decide that the F is more favorable than G if the likelihood of F is greater than likelihood of G. So the very natural value of C is 1. But in this case, if we put some log before it, so it will be 0.
Yeah. Now they discuss some edge cases when C is again equal 1, for example, and let's continue to the next chapter. Here, chapter number 2, they say the notion of consistency. Again, one of the things they want to emphasize in the paper. And in their case, they want to say, okay, now I want to do it in a non-parametric way. Which guarantees would I have that my solution is even coming closer to the best solution possible under the assumption that I have more and more data? So similar to like a consistent estimator, as we talked again in our first episode.
Yeah.
And let's see, they define here 2 types, right, of consistency. Let's see exactly. There are 2 here. They say there are 2 different notions of consistency for sequences of statistical decision function. Again, decision function, you can think about again as some kind of classifier or an algorithm that tells you if data point Z is in class A or B.
Yeah.
And let's see where they define exactly those 2 here. First definition is consistent in the sense of performance characteristics. So again, if I have a non-parametric solution that some algorithm I come up with, what guarantees that the performance will stay the same? Okay, that's the performance characteristic. And they say there's even a more stricter claim, which is definition 2. It means consistency in the sense of decision functions. So the more strict definition says that under the assumption of more data, my non-parametric, let's say, classifier will converge to the best one, which is the maximum likelihood. Not classifier, but ratio. Makes sense? Tell me, Mike, what do you think?
I'm not sure. I have a bit different interpretation. Can I go up, please, to the definition 1? Yeah. Then I look at this definition, and for me, delta is it delta? The delta n.
It's delta 1 and delta 1 and delta 2.
And delta 1 and delta 2 is a kind of random variable, because our decision is invoked on random variable, which is sampled. So actually this decision function is a random variable. Okay, if you think about this delta as a random variable, what you can see here, at least for the best of my knowledge, is just a convergence between the probability functions of these 2 random variables. So now the decision function is a random variable. Okay,
exactly.
We have 2 decision functions. We have 2 random variables, and we demand that the
probability,
that the probability of any value of the first random variable and the second random variable will be arbitrarily close. if you can imagine it in your head, you can just imagine two probability function, two probability distribution, and you just demand here that they are very close. Then I look at this formula. I remember of Kolmogorov Smirnov distance. I'm not sure it is distance between two probability distribution, which is a maximal distance between 2 points of the probability of two probability distribution. And here we require that this distance between distributions is arbitrarily small, can be made arbitrarily small for large n and m. Okay, this is the first one, and the second one is different. I think in one of episodes, I've been talking about. I talked about almost sure convergence, and here what we can see, we can just interpret this delta 1 and delta 2 as two random variables, and here we require that in any case they kind of converge to the same limit, and this is almost sure convergence. It is stricter requirement than the convergence
than the first one. Yeah, but can't you say that the first one is performance, meaning let's say I have the best one is, as we said, maximum likelihood ratio, and you decide if you have the distribution, you decide on a given new point if it's in G or F. That's the best one. So the performance says my new non-parametric decision function I do will, from a performance perspective, will give most probably, that's why it's probability, close to the one that the maximum likelihood gives. That's performance. The second one actually says the decision boundary will be the same in both.
For the n which is large enough.
Yeah, exactly. In both cases, yeah, with n goes to infinity.
Actually, it makes sense. It makes sense. You are looking at it as an engineer, and I'm looking at it as a former mathematician. Although I finished my PhD 18 years ago, but still I'm former mathematician, and I'm thinking about convergence. But your explanations makes a perfect sense now. Now I understand.
Cool. Yeah. Let's continue. Let's see what's important here. Okay, next chapter, consistency for the parametric case. Exactly. And for our listeners, again, we're still not in the non-parametric case. They still didn't introduce their algorithm. They're just giving some guarantees and some, let's say, mathematical formulation of what this kind of algorithm or a decision function should, assuming we have one, how we will behave, let's say, in a sense.
Yeah, they define some mathematical relationships between these non-parametric and parametric cases, I guess.
Yeah, so chapter number 3, consistency for the parametric case. Let's see what they say here. Okay, this is the case for listeners when, similar to what Mike said, like a mixture of Gaussians, etc., where we assume that the distributions of the two classes following, let's say, Gaussian distribution with some mean that we don't know, or some standard deviation that we don't know, and they're defined as theta, and now they say, okay, you can estimate those given the data. So now you get data from the two classes, some m samples from one class, n samples from the other. You can use tools to estimate the, let's say, the standard deviation and the mean, and then you can do maximum likelihood.
By the way, one of the algorithms to estimate in this case, if I'm not terribly wrong, is maximization ME.
Expectation.
Expectation maximization. Yeah, because it can work. You have your variable, which is some mixture of two, maybe totally unrelated distribution, but you still can use expectation maximization to estimate it, Right.
Yeah, we'll get to that paper. It's around the 80s, so we still have time.
Okay.
Okay, I think this is an important part where they give some intuition that's coming closer to nearest neighbor. So they say, our problem is now to find consistent estimates for f of z and g of z. Again, z is our point, and we want to do the likelihood between f of z divided by g of z. And we want to estimate. So they say, we shall, for brevity, consider fz only. And the same applies for g of z. And we fix z. That's the point now we got, the data point, since the argument is the same for each value. Our basic idea is this. The proportion of the m x's which fall in the stated small neighborhood of z may be used to estimate the x probability in that neighborhood, meaning the probability of the x data points that come in from distribution f. The ratio of this estimated probability to the measure of the neighborhood is then an estimate of the average value of fx near z. This is in turn an estimate of f of z itself if we make some assumptions about the smoothness of f. Okay, so to our listeners, they're like saying, okay, it's like, as far as I can tell, Mike, tell me your thoughts. I thought about it like doing some histograms. So I have data points, and now I'm looking in some area and I build a histogram, and then I take the n number of beans, like the bean or bean in the histogram, and like make it smaller and smaller, or I had some kind of this intuition. What do you think?
Yeah, I think one of the intuition is that you just take your point and just you're just looking at the portion of the points which came from distribution f. Okay, and this is the first this is the first line of thinking, and when you have some local estimation of your distribution function. You have some region of function f. You have some samples, and the very intuitive way to estimate this density is just to look at these points and to estimate, make some some interpolation. Okay, or you can just compute the average value of this function. And you can do the same for the function z, for the distribution g.
Okay? Yeah. Okay. Yeah. Thank you for that. Now it makes sense, because I got it, because I want at the end to do f of z divided by g of z.
Yeah.
Right. So in order to calculate f of z, I just look at the small neighborhood around z and try to estimate this number.
Yeah.
And I have a few data points around it.
Yeah, exactly.
Cool.
I think it is quite important paragraph. Can you go up?
Which
no,
one?
not Lebesgue measure. No, this one.
Yeah, I saw Lebesgue measure. My blood pressure rose up. And,
I think it is quite important, because
you can read what you see.
I'll read it loudly. It is obvious that we can't hope to estimate f of z from this sequence of x1 to xm unless some continuity assumption is made, and for otherwise we could alter f of z arbitrarily without in any way changing the distribution of this sequence, and thus without changing the distribution of any sequence of estimates based on this sequence. And for me as a mathematician, it's quite an important assumption. So if your
tell me.
Yeah, if your probability function is very wild and it is changing wildly, even in very small neighborhood of this point, Then what are you doing? You just averaging 1 in million. What is the average of one? You have two people. One have an income of $1, and the second have an income of $1 million, and the average is $500,000, but totally meaningless. And this continuity in assumptions ensures that you don't get to this situation, and or alternatively, you can just shrink your neighborhood to ensure that this distribution function or density function behaves more or less smoothly. You know, as a foreign mathematicians, I couldn't miss it.
For me, I read it. I'm like, okay, yeah, cool. You know, I'm thinking as an engineer. Oh yeah, smoothness. It means I don't have high frequency in my data.
Yeah. And it is exactly this. But for mathematician, you have a bit another image in the head.
Okay, I won't go into Lebesgue measure and stuff like that, but soon we'll get to the important point. Where they actually start to introduce some kind of nearest neighbors. Here, I think it's here. They say, as a first step in answering these questions, observe that we may, by means of preliminary transformation, reduce our space from p dimension to 1. Again, because we said those data points could be in p dimensions. And let rho, x of y, denote a non-negative real-valued function of pair x and y. So again, this is just a distance metric.
Yeah.
So now between a point x and y, rho returns some distance metric, whatever you want it to be. And they say here, for example, they show the Euclid. Is it the Euclidean one? No, it's the p.
No. It's even. I'm not sure it's even LP. It is just a pth root of x minus y. It is not LP, but you know, it is some kind of distance.
Yeah. So again, rho is the distance function between x and y.
Yeah.
We now replace the problem of deciding whether f of z or c g of z is larger by the problem of deciding whether fz of 0 or cgz of 0 is larger. Again, because we're down to one dimension. So now we need to estimate f of z in this one dimension.
Yes.
And then replace the samples. We have m samples, x1 to xm from one distribution and y1 to yn from another, by those distance functions. So rho x1 z that we got, and etc. Rho x2 z. So z is the data point we want to classify. So now we measure the distance between the z to all of our other points that we have from the two classes.
Yes.
They say we may now, without real loss of generality, assume that f and g are densities of non-negative univariate random variables. Okay, let's random that and let's get to the important part.
By the way, it's a small remark. In plain English, it says that we decide that z comes from f if it is closer in average to all the points of sampled from f, and they say that z is from g if z is closer in average to the points sampled from G. It is just in plain English, you know. It is very intuitive.
Yeah. So again, this is like, in a sense, k nearest neighbor. Still, we didn't define k, but they say calculate the distance from your data point to the two classes and decide if it's closer to this class or to the other one, as Mike said. And now they introduce the k. They say define u capital U as the kth smallest value of combined samples. So they say, okay, you decide on k, and they give you later some intuition if it should be small or large. But let's say you define k, you calculate the distance between your data point and all the other points of the two classes, and you take the k largest distance or smallest, depends. Let's say k closest other data points.
Yeah.
Okay, from both classes. And they say, let's define m as a number of x's that are in class 1, and n the number of y's, meaning those in class 2. And now they normalize it because, okay, maybe you decided to do k 100, and one class got 90 there, and the other class got 10 data points that are closest. So now you need to like normalize by this ratio in order to decide if you're in class 1 or in class 2.
Yeah,
so that's what they do here.
Yeah. By the way, I want to explain it to maybe our listeners in Spotify who doesn't see this paper. I can explain it very simply in a plain English. You are just taking k points from x, y, from x from the distribution f and from the distribution y, which is closest to z. Okay, we just picked k points from the both distributions f and g.
But you need to calculate everything.
Yeah.
First step is calculate all the distances. Then take k, which are the closest.
Yeah, and then you decide, if you have more points from y in this neighborhood, which among these points, you decide that z came from f, and then there are more points from g. You decide that z came from g, and it is exactly k nearest neighbors. It is exactly this algorithm. And by the way, all what I told you now follows from this assumption of z equals to 0. Okay, it may look very complicated, but it is simple as this. It is just k nearest neighbors.
Yeah, important point, but you need to normalize, Mike.
Yeah.
Right? If you have too many...
I need to compute the ratio. Then I compute the ratio, automatically it is normalized, right? Or I miss anything?
No, I think you need, let's say you have, you chose k to be 100, and you got, 90 of the data points are close to this class, and 10 are close to this. First, I think you normalize it by the number. So you have the same number of samples, and then you look at the distance, and you see which one is closer.
I'm not sure, because take a look at this.
Because why otherwise normalize? You can stop here. You can say m is the number of x's inside U, n is the number of y's. Then you do just the ratio. But you can see that the normalize by small m and small n, meaning you normalize by how many data points in total you have from x and y.
You are right. If the purpose is to estimate f of 0, because we assume that z is equals to 0 because we are talking about differences. If the purpose is to estimate f of 0 and g of 0, you are totally spot on. But here I'm thinking about the decision function, and the decision function is a ratio between f of 0 and g of 0. And then you do this ratio, the both of them are divided by u. So this u is going out. So it becomes irrelevant. And then you just decide on this ratio. And this ratio actually is k-means, more points from f, you decide on f. More points from g, you decide on g. Am I missing anything?
No, I understand what you're saying. I'm trying to think if it makes sense.
There are two different
Here,
things, you know,
here, but
estimation.
here they say it. Let's read. They say it exactly.
Okay.
Choose k. That's the end of the paper. A positive integer which is large but small compared to the sample sizes. Step 1. Specify a metric in the metric space. For example, ordinary including distance. That's your distance metric.
Yeah.
Pool the two samples to find of the k values in the pooled samples which are nearest to z. The number m, which are x's, and the rest are y's, which is n. Proceed with the likelihood ratio discrimination using, however, m capital, which is the number that from class 1, divided by m, which is the total number.
This
samples.
normalization, right?
Yeah.
Okay. So you're right. It is my mistake. You need to normalize. If you have much more points from F
Exactly.
than G, you need to normalize. Now I understand. Yeah. I totally missed this normalization. You're right.
Yeah, that's what I meant. If you have like 90 points and 10, you need to somehow take into account.
Yeah, if you have 90 points of F and 10 points of G, there is more chance that you will have points. If you know, if stuff is, if the distribution is stationary, there's more chance that you get from F than you get from G.
Yeah.
You know? So it is very important. Yeah, you're correct. My wrong.
Yeah, so that's like the last sentence of the paper. They summarize their algorithm, and they show the references, which are 3 papers, and 2 of them we reviewed, which is cool.
2 of them? Did they?
Like
did
the
they
first one.
Yeah.
We did a similar one to the first one. Another Niemann and Pearson when they did maximum likelihood.
Yeah, exactly.
Between deciding about distributions. Cool. So this was the end of the paper. Your thoughts, Mike, about how relevant it is to your job, our jobs.
K-means is K nearest neighbor. Sorry, KNN, not K-means. Okay, K nearest neighbor is one of the most important and the most intuitive algorithm in clustering in the unsupervised case. And I personally used it once in a quite successive manner. Although I required to somehow invent quite complicated distance functions because I have very special features of my problem. This was on graphs. Okay, we're not going to delve into it because most of it I forgot, but I remember what I thought a lot about some proper distance functions. Because the distance function is a core of this method. Okay, everything, like in any other clustering algorithm, depends on the distance function. The paper is not discussing it, but it is a crucial detail. If you change your distance function, everything changes. And
I have a question then.
Yeah.
What about retrieval augmented generation, right? RAG.
Yeah.
What do you do there? You get a prompt, right? You embed it, and then you look for a distance between that to the other ones. So in the sense, you're doing some kind of nearest neighbor. Maybe K1. No, I cannot say that.
No, I'm not sure. I think you just in the naive case, I think nobody is doing like that now because there are many generalizations and sophistications there. But in the naive case, you need for a given prompt, for a given question, you need to pick the document which is the most relevant for this question, and it is done according to the distance between the embedding of this request and the document.
So
and
if you have a database and so you have one vector and then you have a database of a lot of vectors, how do you find the closest one? It's not some kind of.
But you know, the paper is not talking about how to find the closest.
That's true.
It is not discussing some some sorting algorithm. It assumes that samples are small enough. It was 8 years ago. The computers were not so powerful as today. It is not talking about how to measure all these distances. By the way, I think in modern implementations of k-nearest neighbors, I don't think that if you have samples of 10 billions, and it is a quite common case in some scenarios, and you don't compute all distances. You do some approximations. But here I think it is not a point in the RAGs. You just picking the k closest documents. You use top k, but you don't decide to. You just take.
I understand. Yeah, it's not the same problem. I agree.
Yeah, it's not the same problem.
But the idea of looking at distance metrics to decide about if it's this or that is similar.
Yeah. Actually, it is somehow. I think now understand what you're talking about. Actually, it is very good that we joined forces on this podcast, because your state of mind, your way of mind is more engineering than mine. Although I'm almost 20 years not doing a pure math, but still, I was doing it for many years. And when we join forces, your ideas come from different places than mine, and this combination is quite good. Now I understand you. So conceptually, you have some similarity, you have some inspiration from this.
Yeah, that's what I meant. I didn't mean it's exactly k-nearest neighbors, but the idea of using some metric to find distances and decide stuff.
By the way, if we are talking about k-nearest neighbors, the paper is not discussing how to choose k.
That's right.
Yeah, you can choose k equal to 1, and then you just decide on the most closest point. If the closest point to z is from x, then it is distributed as x. If it is from y, and you can choose k equal to the sample itself. Okay, so both of these choices are very bad. Okay, so there is some clever choices of k in order not to do overfitting and also not to do underfitting. Now I'm talking about clustering. So there are some works. Maybe we'll discuss a couple of them, which discuss how to choose k in kind of optimal fashion.
If it's supervised, you can learn k on your train set and and use it for the test.
Yes.
Perfect. So thank you for this episode. It was fun.
Yeah.
And a great paper from 1951. And guess I'll see you and the listeners next time.
And hopefully Nir.
Yeah, and we miss Nir. So hopefully next time he'll be with us.
Bye-bye.
Bye, everyone.